Okay, really good problem for testing your knowledge of function and function notation. So, a function that expresses the area of a square as a function of a side length s. So whenever you're defining a function, it's crucial. So the number one thing that you're asking yourself is what? You're defining a function. Anybody? Have we learned anything? Yeah, we're going to define a function. So what's the key ingredients if we're defining a function? What do we have to know and be very confident of? What the input quantity is and what the output quantity is. If you don't have those straight, you're just gonna flail. You'll never make it through this. You got to be absolutely confident what's the input and what's the output. So, reading this statement, the function that expresses the area of a square as a function of the side length s. What's the input? And what's the output? Area of a square as a function of its side length. So input is side length of the square. Okay? Output, area of that square. So you can never waver on this. If you waver on what's going on here and you're not sure about function notation, you'll just struggle the whole way. But if you're confident about this and you know how function notation works, then you're gonna succeed. Okay? So we want to define a function f. So the name is f. Our input variable is s equals. Now we need a rule that takes our input quantity s and gives us area of a square. So that's just an easy geometry formula, right? S squared. That's why we call raising something to the second power squared. Did you know that? That's why we call it squared, because it's the area of a square. Squaring something gives you the area of a square. So that's why to the second power, raising it to, that's why we call it squared. Okay, so use your function to express the area of a square that's 25 meters when the side length is 5. So over here we need function notation f of what? We're saying f of 5 equals 25. F of 5 is the output when the input is 5. F of 5 is a value. It's the output. F is not a value, right? F is the whole function. It's everything about the function. It's like a label, like a name. Okay? So you never say f equals something, but you would say f of 5. That's output. F of 5 equals 25. Okay, doing good? Expression. How much larger an area of a square with side length 49 is than an area with square length 36? So what are we really talking about here? Saying how much larger one quantity is than another. It's the difference, right? It's like a change. It's like a change in area. So what's our bigger square? Has a side length of? Okay, so here's where we got to know input and output. What's 49? Is that the side length or the area? No, it says with side length 49. Side length 49. So is that input or output? 49 is the input. So you're thinking, oh, that's 7 squared. So 49 is the area. But it's side length. You got to read carefully. Side length 49. And side length is our input. It goes f of input, right? So they tried to trick you to see if you're going to read carefully. All right? How much bigger that is than the area of square side length 36. F of 36, not f of 6. F of 36. They're giving you side lengths. Side length is input. Input goes in the parentheses. Okay, so now we're going to write this statement. Again, you got to be firm on your input and output. The total area of two squares, one with side length 4, the other with side length 12, is twice the area. So let's just stop right there. So we're going to just mathematically create a statement that just mimics this English statement. So we're going to create this statement. It's just exactly the same. So we're going to total up two areas. So we totaling up inputs or outputs? We're going to total up outputs. We know we represent output with function notation. So it's going to be f of something plus f of something. So what are we going to add up? Total area, one with side length 4. So f of what? 4. And the other with side length 12. Telling you what the input is. Input is side length. Is, what's is? Equals twice the area of side length y meters. So now we're going to say is, yeah, so it's going to be 2 times the area of another square. What's its side length? Y. So we're just writing this out, just as it's stated in English. The area of side length 4 plus the area of side length 12 equals 2 times the square of area side length y. So then this is just algebra. So you would find f of 4, f of 12, divide by 2, take the square root, so that you can do part E on your own. How do we do? Okay, got him. So really, this is, get that out there. It's really about being very, very confident when you're defining and working with a function. It's all about being very confident. What's the input quantity? What's the output quantity? Reading carefully and using the function notation correctly. Input goes into parentheses, right? The output is f of that thing in parentheses, is the output. Next one. Okay, so yeah. So the revenue functions, total cost function, f of x, is going to be the startup cost, 10,000, plus every computer costs 550x. Okay, so there's our cost. I'm going fast. Revenue is g. So g of x is going to equal 1199.99x. That's how the revenue is 1199.99 for every computer. So that's revenue and cost. I know I went fast, but that's because I want to get to this. Function notation. So this is changes. C and D is looking at changes in outputs. So you're going to have like f of something minus f of something, right? And g of something minus g of something. So when you do the change in output, it's the difference of output values. It's the change in output. Final minus initial. Okay, so H. Total profit as a function of x. Well, so profit is going to be your revenue. Your revenue was the 1199. Oh, this is in terms of f and g. So it's going to be, we're going to use f and g now. So what was the revenue, all the money you bring in, minus the cost. So how much money did we bring in? Wasn't that the revenue? So for x computers made and sold, you're going to get g of x revenue. And how much was the cost? fx. So for x computers built and sold, you're going to get gx revenue, g of x, and f of x in costs. So g of x minus f of x will give you your profit, how much you can take home. Who asked for it? Does that?
Yeah, I had put h of g of x minus f of x. I combined the two, so is that something completely different?
Well, first of all, you're defining h. You're defining h. That means h of x equals something.
Okay.
You're just defining the function h. And we're not you're not plugging profit or revenue into something else. So h of g of x or h of f of x would be like taking the revenue or taking the cost and then plugging that into another function. We're not doing that here. We're just trying to come up with how do we compute the profit, which is revenue minus cost. Revenue minus cost. Okay. And then you had some warm-up exercises with composition. So we're going to keep going with composition here. Let's see. So get your Pathways workbook out and look on this page here. So it's in Module 3, Investigation 4, number 2. It should start with a pebble thrown in the lake. Is that right?
Page 92.
Thank you. Page 92. A pebble thrown into a lake. The radius of the ripple travels outward at 0.7 meters per second. Your goal is to determine the area inside the ripple in terms of the number of seconds elapsed since the pebble hit the water. So that's the setup. Okay, you're going to throw a pebble into the lake, and then as soon as it hits, then you're going to have a ripple that travels out and at 0.7 meters per second. And that's a circle, right? So that circle is going to grow as time goes by. So I want you to go to part D. Skip to part D. We're going to start by defining these functions. So, for part D, super important a skill that you need to be able to have. Given a setup of a description of a function, can you define it? So define it mathematically. Write it looks like an equation, right? A function definition looks like an equation. Can you write, for instance, P of A? So here's an example of a function definition. P of A equals, square root of A plus 3 plus A cubed. Right? That's an example of, we're defining the function P. I'm defining the function P. What are the elements of that? There's 4 things. There's input, there's output, there's the name, and there's the rule. What's the input of this function I've defined here? A. What's the output? P of A. What's the name of the function? P. And what's the rule? The thing on the right, right? This thing is the rule. The rule tells us, given an input, how we get the corresponding output. Okay? That's what you're doing here. Your answer will be something like this for both of these. Defining a function named f, defining a function named g. Okay? This is the model of a function definition. So see if you can do it. I'm going to start handing back some homework. Just part D. Just part D. Okay, so this homework is alphabetical by last name. We just pass it, you just pull yours out. Okay? These all hand back. Okay. Stay focused on the task at hand. Just take the graded work and put it away and look at it later, okay? Please. How did glance at the score and then look it over later. Daniel Almeida. Pierce. Annette. Comment. Aisha. Aisha here? Lauren Becker. Lauren. Megan. Kristen. Percy. Tyler. Hassan. Jared. Alexis. Bradley. Bradley. Bill, come. Alexandra Cohen. Elise. Darwish. Where's Alexandra? Darwish. No Darwish? Shannon. No Shannon? Marquise. So, to define a function is the very first thing you're going to do. The very first thing you're going to do before you do anything else. What's the input quantity? What's the output quantity? And then make sure it's locked in. F's input is this. F's output is this. And then don't vary from that. Don't falter. Nicole. Tiana. Bella. Nada. Javier. Chris. Francis. Get the input and output quantities for that. What's the input and what's the output? Write it down. Write it down. Marina. Chris. Okay, what's the input for function f? Time since the pebble hit the water. Remember, be specific. And I'll address it later. The time since the pebble hit the water. What's the output?
Radius.
Time since pebble hit the water. In seconds. All right, that is, and they told us that's t. And then output. R is the output. It's the radius of the ripple. In meters. Okay, so now can we? There's 4 parts to the function definition: the input, the output, the name, and the rule. What's the name? F. So it's going to be f of what? F of t or f of r? See how easy that was? So when we lock down what input is and output. But if you just start the problem, you go f of t, r, I don't know. Lock it in. Input is this. Output is this. Then f of piece of cake. F of t. And then so what is the rule that gives us the output radius given the input time? Every second, it grows by 0.7 meters. So you're going to take the number of seconds and multiply by 0.07 to get the number of meters. So where's the r in this? Where's the r in this definition? F of t is the same as r. If you wanted, you could write r equals f of t. You don't have to. But we don't have to write the r, but we know that f of t, that output, that's r. That's r.
So f of t equals r would be correct as
No,
well?
r is not the rule. R is a variable for the output. The rule has to be in terms of the input. 0.7t, that's the rule. But if we wanted, you could also include in this definition, over to the left, you could say, optional, you could say r equals, because the output is r. But not required. The f of t equals 0.7t, that's the definition. If we wanted to, we could also say r equals f of t. Okay, so what about G? Input and output. Then you're going to write it. I'll hand back a few more quizzes. So those who were stuck on part 1, now you can make progress on part 2. Okay? Where's Adam Goldberg?
Right here.
Serena Gomez. Aja. Aja here. Brittany Hale. David. JJ.
Yeah.
Christian Wayne. Christian here. Vanessa. Jessica. Justin. I'm coming. Rainy. Hunter. Sorry. Joaquin. Justin's way over there, right? Andy. Okay, if you're done with those two, then I have a follow-up question. What would make sense? F of g of x or g of f of x? If you're still working on g, finish g. But then if you're both done with both, what would make sense? F of g of x or g of f of x? Andy. Tyler. Karen. Juice. Katie. Katie here? Francis. Francis here? Okay. So you should have gotten for G. Input is. What's the input? Radius. Output is? Area. Okay. What's the rule for using R that gives us the area within the ripple? Another geometry formula. We just use it. So pi r squared is the rule that would give us area as output for the input of radius. Okay, so now I asked the question. I said, what makes sense? F of g of x or g of f of x? F of g of x or g of f of x? People are saying g of f of x. And what's the key to that? What's the key to this making sense?
F of x is no.
Okay. F of x, is it an output or an input? Is f of x an output or an input? It's both. Just looking at f, it's what? It's the what of f? The output of f. But in this expression, it's also the input of g. And those have to, that quantity that's the output of f has to match the quantity that's the input of g in order for it to make sense. What's happening with f of g? What's the output of g? Output of g is area. So we're taking f and we're saying here area, here f function, take area. What does it say? What does f want? What is its function? It takes what?
Radius.
It takes time. It takes time and it gives radius. We're trying to give it area. But that function accepts time as the input quantity, and its function is then to give the corresponding radius. And we're trying to give it an area. So f says, sorry, that's not my function. I don't do that. So this doesn't make sense. Right? Functions have a function. The function of f is to take time and give radius. So we give it area. It says, that doesn't make sense to me. But this is good because the function of g is to take what? What does g take? It takes radius. And that's what f puts out. So, perfect. F gives radius. G takes radius. We've got, it works. Okay, so let's examine this g of f of x. That's what we're really interested in here. Any questions on defining the functions? Are we good? Defining f and g. Okay, so take a look at this. Here's a picture of what we just talked about. We've got our, what comes first? We said g of f, right? Is that what we said? Make sense? So g of f, what function comes first? F comes first, right? And this is our f function, 0.7t. Okay, so what I want you to do, so this is the idea that we put time into the f function. This is f, the f machine. It gives us radius. We put radius into the g machine, and it gives area. So a two-step process, right? And so I want you to find the area of the ripple at 4.2 seconds. After impact, after hitting the water. Okay, and then represent that answer with function notation. So first get the number. What will the area be? I want a number. I want a number. What will that area be? 4.2 seconds after the pebble hits the water. And then once you have that number, so represent that number using function notation. How could you represent that answer with function notation? Okay, I'll hand out a few more. Is Flora here today? Flora. I know you. Go. Evan Peterson. And Angelica. Laura. Anthony Rodriguez. Nisha. Kevin Peterson. Kevin. Nisha. Angelica. Jordan, Rumba. Jordan, go Jordan. Right. Taylor. Danielle. Kyle Sorensen. Or Kylie. Kyle or Kylie. Sorensen, Colleen. Alex. Marlene. Denise. Sure. Two here. Denise. Alex. What's up? Paula. Paula Valenzuela. Araceli. Scott Hooker. Matt. Listener. Anna. Dustin. Is that Araceli? Araceli. Thanks. Okay, what was the area? What's the number for the area? What'd you get? 27 point something? What is it? 27.15. What's the units? Meters squared. Okay? Did you get that?
Yes.
How do we represent that with function notation? So 27.15 meters squared equals what? Okay, a couple people are saying it. So what did we do? We took the 4.2 and we plugged it into F. And then we took that result and plugged it into G of F of 4.2. How many people got it before I started asking about it? Okay, not enough. Got to get the point here. What did we do? We put 4.2 into F, F of 4.2, took F of 4.2, put it into G. That's how we represent that in function notation. Okay, so now I want to show you something else here. So can we also say that the output of f is always 0.7t, right? Isn't the output of f always 0.7t? So watch this. So then if that's also a representation of radius, and we know that g is a function of radius, so I can take isn't this a valid statement then? Isn't that valid? 0.7t is radius. So and g takes radius. Okay, it's okay. Yeah, 0.7t is radius. So I'm going to take a radius value, put it into g because that's what g accepts. And what does g say to do? G says to take whatever the input is, r, square it and multiply by pi, right? That's what the rule for g says. Take the input and square it and multiply by pi. So I'm going to do that. I'm going to take the input, 0.7t, and I'm going to square it and then multiply by pi. Is that consistent with the rule for g? Yes. I took the input, I squared it, and so then I get this new rule, which turns out to be 0.49 pi t squared. Okay, and that's what I got when I did g of f of t. But this is a new rule, so we can just call it its own function. We could call it, say, h of t. What's the input into h? Time. And what's the output of h? Area of the ripple. We've eliminated the middleman. Who was the middleman that we eliminated by creating the h function? We took the radius out of the picture, and now we're going straight with h. We go straight from time to area. So it's like, instead of two machines in succession, it's like one big machine. 0.49 pi t squared. This is the h function. It's the h machine. It takes time, gives it this rule, and it spits out area. So now I want you to do h of 4.2. Find h of 4.2. The output of h when the input is 4.2. What's the output of h when the input is 4.2? You should know what it is already. No calculator required, right? What should it be? 27 point. So check it, okay? So if you're putting it in, hopefully that's because you just want to check it. Because you already knew what the answer was, but you just want to make sure. So you put the 4.2 in, and you get 27.15 meters squared. So what do we do? So this came from, where did this h function come from? It came from the two-step process of f of t, that's a radius, putting it into g. And by putting the rule for f in there, we got a rule for the overall single function process, which was this one down here, 0.49 pi t squared. So again, this is this idea of we can represent composition as a two-step process. Time gives radius, second step, radius gives area. Or we can generate a new function that does it all in one step. Time results in area. Or time maps to area. Eliminate the middleman, right? Eliminate the middleman of radius. Okay, so there's somewhere, if you flip a few pages forward, there's this problem here. Is it number 7 in your book? Anyone find it? What page is it on? 96. So I'm going to skip right to part C. So C says we want to make a single rule out of this two-step process. H of x first, take the output of H, make it the input of G to get the final output. So we want to create a rule that would do that two-step process all in one step. So I want you to do part C. Started. What did we do in that area? We took that rule, that 0.7t, we put the rule in. So that's what you can do. Put the rule for h of x into g. What's the rule for h of x? X over 4. And so now that is, you think of that as your new input into g. Your new input into g is x over 4. And what does g say to do? G says take the input and multiply by 2, then add 9. So you're going to do that. You're going to take the x over 4. You're going to multiply it by 2, and you're going to add 9. And so we could do 1/2 x if we want to simplify that. It's not required, but just to make it a little cleaner, 1/2 x plus 9. So this now is the single step version of g of h of x. Does it eliminate this single step rule? Does it eliminate the input or the output of h? What does it eliminate? The input or output of h? The middleman is going to be what? The output of h, which is also the input of g. That's gone now. We just have the initial input of the initial input of h, and the final output of g in one step. Okay, so now in problems like this, where you don't have defined quantities, so these are just function definitions, we have no idea if it's time, distance, temperature, height, volume, we don't know. We could do g of h of x, and then we could turn it around and say, okay, let's make a new thing, q of x, and we can say q of x is h of g of x. So this is, we can mathematically do this because we're not really, in this context, we don't really care about the quantities, making sure that output matches the input. So this is valid, all right? So without quantities involved, it's valid to find g of h of x and then also h of g of x. So go for it. So find h of g of x. And we'll call that new function q. Does it make sense? So with no quantities involved, we can do it either way. Two x plus 9. So what does h say to do to the input? What does h say to do to the input? Divide it by 4. We're going to take the input. This says take the input and divide it by 4. What's our input? Take the input, divide it by 4. So look, that's q of x. Was g of h of x the same function as h of g of x? Totally different, okay? You get a totally different function if you reverse the order of the process, right? If you start with h and then do g, your overall effect is 1/2 x plus 9. If you start with g and then do h, the overall effect is 2x plus 9 all over 4. So totally different when you switch the process. Question, Tyler?
Can you simplify it? Can you simplify
Sure, you could, yeah, if you wanted to do, you could do 1/2.
Should we do it, or?
It doesn't matter. If it's asked for, this is the most, what I'm showing here is the very most important part. So the simplification is kind of less important. But if you wanted to, it would be 1/2 x plus 9/4 is 2.25. But less important. It's less important. So getting to this is the crucial step. Okay. Questions on that? All right, we're going to start a new topic here. What's that? It's 50. Okay, so this is way ahead somewhere. I think it's in Investigation 5. So flip ahead to Investigation 5. You find this is when traveling outside the United States, number 2. What page is on it? 102, page 102. Okay, so they've defined, this is about conversion between Celsius and Fahrenheit degrees. So you're outside the United States, you understand Fahrenheit, you know what 70 feels like, you know what 35 feels like, but in most of the rest of the world they use Celsius. So they're going to say 35 Celsius. I don't know, sounds kind of cold, but who knows? Or 100 Celsius. Sounds really hot, I don't know. So this function then takes the Celsius degrees What's the input? The input is Celsius, the temperature in Celsius, and the output is the Fahrenheit temperature, okay? So what's the meaning of G100? First of all, tell the person next to you what's the meaning of G100, and then find the value of G100. So what's the meaning of G100? What's the value of G100? Go. Okay, where's Taylor? Taylor, you're up. Tell me the meaning. What is, when you just see the symbols, this expression G of 100, what does that mean?
It means that the output in Fahrenheit, or you get the output in Fahrenheit when the input of G is 100 degrees Celsius.
Okay, so pretty good. 98, A plus. Just one thing. So you'll get, so it sounds like you're going to do something, right? But G of 100 just is something. It is the output. And so it's a degrees, what? Degrees Fahrenheit when it's 100 degrees Celsius. Or it's the output when the input is 100, which is a degrees Fahrenheit when it's 100 degrees Celsius. And you guys found it to be what? 212. So then you turn to the person next to you who said it's 100 degrees out, 100 Celsius, and you say, you're crazy, right? We wouldn't be alive, or we'd be fighting for our life, okay? Really, this is not like temperature, in terms of air temperature, right? This might be measuring what? Like water that's in a kettle or something, or in a pot. You're boiling water. All right? So going on to the next page here. So if the function g of c takes Celsius and gives Fahrenheit, how does it do that? So let's write out the steps. How does it take Celsius and give Fahrenheit? What does it do first to the Celsius? It multiplies Celsius by 9/5. That's the first step in what it does to convert to Fahrenheit. And then what happens? And then adds that to 32. So this is the process, how the rule describes the process of starting with Celsius and getting to Fahrenheit. So what if we wanted a function called h that takes Fahrenheit and gives Celsius. Wouldn't it kind of do this in reverse? Wouldn't it do this process in reverse? So if you had the Fahrenheit, so you got Celsius, you multiply by 9/5, then you add 32. So now if we want to get the Fahrenheit, what are we going to do first? We're going to run this backwards, right? We're going to run this thing backwards. So what's the first thing that you should do to Fahrenheit? Minus 32, right? So if we're going to run this backwards, we're going to start with Fahrenheit and try to get back to Celsius. We've got to take that Fahrenheit and we've got to subtract 32. All right, and then we take that number and do what? Divide by 9/5, right? So we're going to, if we multiplied by 9/5 and we added 32 to get Fahrenheit, now if we have Fahrenheit, we're going to first subtract 32 and then divide by 9/5, right? This should make sense. Divide that by 9/5. Does it make sense? It's like we're undoing what we did. We did something to Celsius to get Fahrenheit, and then what would we need to do to undo that or go backwards and get Celsius from Fahrenheit? So now based on this, write the rule for h. So h is this function. So based on our two-step process there that we just wrote out in words, what's the rule for f? Piece of cake, right? You're going to take f and do what? Subtract 32, and then divide that by, look, we just made the function that takes what and gives what? This function now starts with Fahrenheit and gives Celsius. It's the reverse deal of this one. It's the backwards deal of this one. Okay, so if that's the case, coming up here, if I were to take a Celsius temperature and get the corresponding Fahrenheit, that's what G of C is, right? What if I took that Fahrenheit? So let's call it something here. Like instead of C, generically we meant C meant any temperature. So let's call this now, say, Y or W. So I'm going to take W as some Celsius temperature, right? If I put it into G, G will give me corresponding Fahrenheit. So if that's a corresponding Fahrenheit, I could put it into H, right? I could do a composition, since the output of G, Fahrenheit, is also the input of H, Fahrenheit. And if I do that, what will I get? I'll get Celsius, or will I get Celsius or Fahrenheit? Remember, W was some temperature in Celsius. That's what G takes. G of W is going to be what? The corresponding Fahrenheit. I'm going to put that Fahrenheit into H, and the output of H will give me? What temperature in Celsius will it give me? W, the same one we started with. So now, I want you to prove it. Meaning, do the math. So we know it makes sense that if we put W into the Celsius, W into the G function, it gives us Fahrenheit, the corresponding Fahrenheit. And then you put that Fahrenheit into H, it should give us back that original Celsius. But so now let's practice the algebra that proves that, right? So this is what we did in the previous exercise. Remember doing that? what do? You start by doing what? Do h of the rule of g. Remember this? We just did this about 5-10 minutes ago. You're going to start by doing h of the rule of g. And then you're going to work out the algebra. And what do we expect in the end? We ought to get w. We ought to get w. Okay, go. See if you can do it. So practicing this technique of, you've got a composition. We want to find a single rule for the whole composition. Okay, I'm going to call on somebody. So everyone's working on this. I'm just going to call on you. Be ready to answer. Everyone's going to do this. It work? Okay, Muliz, you're up. Did you get started on it? Just get started. So we'll start with the rule of g. The rule of g when w is the input. So what would the rule of g be when the w is the input? Muliz. That's it. Well, that's the start. That's my question. Okay. So now we're going to evaluate h, thinking about this whole thing as the input quantity, right? And what does h say to do to the input? What does h say to do to the input? Right? Yeah. So we're going to take the input, which is now 9. This whole thing, 9/5 32 plus 32, and you said subtract 32 and yeah. Okay, so we just got like kind of one step in between. So how can we simplify the numerator? That equals 32 minus 32 is 0. Good. Equals? Did it. So that's the algebra behind it, right? We took the rule for g, and we cranked it through h, and we got what we expected. That if you take a Celsius temperature, find its Fahrenheit, g of w, and then take that Fahrenheit and put in h, which finds the corresponding Celsius, you're just going to get back what you started. Okay, so now look on page. Number 7 is about a volume of a sphere. Find number 7 that's about the volume of a sphere. Did you find it? So we're going to find, so ignore the questions for domain and range. let's see, what's question C? Does it say find the inverse? All right, so first we're going to write out the process of F. What does the rule of F say that we do to the input to get the output? What's the first thing that the process of F says to do to the input? Cube it. That's different than multiplying by 3, right? We're going to cube it. We're going to multiply it by itself 3 times. Did you say multiply by 3? But we're going to start with the input. What do we do to the input? You see, we're going to cube the input first. So the process of F is first to cube the input. And then after, what do we do with that then? Then we multiply by. Well, we can do it. So we can think of this all as one number. Okay, let's do it all at once. So we can multiply by 4/3 pi. So what would the inverse process? And so here's the notation for inverse. It's not f to the -1. Okay, that's not an exponent. This is notation that means the inverse function of f. So the process of f inverse, write it out. What would come first to reverse or undo this process? What would you do first? Divide by 4/3 pi. So you're going to divide by 4/3 pi. And then take the cube root of that. Cube root of that. Okay, so now we're going to write f inverse of x. And then talk about one more thing, and then we'll go. So what are you going to do to x? This is the inverse process of f. You're going to start with x and do what? Divide by 4/3 pi. And then take the cube root of that whole thing. Okay, now notice, this is a function for the radius. It says gives the volume of a sphere as a function of its radius length. So which quantity is the input of f? Which quantity is the input of f? Radius. So what does x represent? Radius. Just give me 30 more seconds, please, of your full attention. Radius is the input into the f function, represented by x. Is x in this one radius? No, it's like the output of f. What was the output of this? Volume. So what does x mean in f inverse? Here it means volume. So this is, again, you've got to keep your quantities straight. And what's the output of f inverse? Radius. It reversed the process. The inverse function takes volume input and gives radius, whereas the initial function took radius and gave volume as output. So x is conventionally used as input always. So you really have to know the context, what it means. Here x means radius. Here x means volume. Okay? So that's important that you see that.